Hi everyone, welcome to BCodeTube. In this series, we are creating neural network to read the MNIST database, the handwritten digits database. And we are creating the same algorithm in both C++ and then the same algorithm in Python. We already look how to create a custom neural network, how to add PyTorch into our network, and today we are gonna load the data in PyTorch using batches. This will speed up a lot the process. So in this video we are gonna use batches. So we are gonna load batches for the train and test data. We are gonna create the model, train the batches, test is batches. We are gonna save and load a model, and we are gonna check if CUDA is available or not. Here I'm back to the project on Linux. Let me revert here these options as I was working on the Windows. So to start with the batches, I'm gonna create new files. For both Python and C++. Let's start with the Python first. First, we are gonna import everything we are gonna need. For the INI, I'm gonna create a new section there. So I added here a section just for the torch. This is gonna split our data into batches of 64 images each. I'm gonna run only 2 epochs just for testing. This is gonna be where we are gonna save our model in C++ and in Python, and the location where you're gonna save it. Here I also have to change because I was on my Windows machine. All right. So here we are gonna load our training data. I put here download files because we already downloaded here in the downloader folder script on our first video, and converting it to tensor. And this Python data, when we pass we are gonna pass just here the MNIST data folder, because inside the library it's hard coded this path MNIST raw. So just pass until the MNIST data where you put your files, and this is the train data. So it's gonna load only the train data here in this variable. And to load the test data, just change the train to false. Here we are splitting the data into batches based on the passed batch size. And here we can take a look on how is this shaped. So we take one batch and we print the shape. So one batch has 64 images. one channel color, it's only black and white, and 28 height, 28 width. It's these are the image sizes. And our Y, or our label, we have 64 labels, and they are saved as integer values. And for C++, let's include what we are going to need. We open the ini file. We grab the values from the ini file. The difference here from the Python is that Python uses the root here and the MNIST data, while C++ we still need to send all the way back to the raw folder. Then and also the save, when we are gonna save the model, the file is different from Python and C++. So here we load the train data, and here we load the test data. So the difference is that we have to pass here that the mode is test. Here we are splitting the data in batch sizes with this make data loader function. We pass the training data, indicating that we are mapping as a stack. And just to get one value here, we are looping the test dataset, but we break right at the first one. I want to get just the same shapes here. On our CMake file, we need to add another executable. Like this. And we need to install. It's the same here. Have to reconfigure. Okay, let's build. Oh, okay. Here I was on Windows. I have to revert here. Let's build again. To avoid this, we can do something like this: win32 else and if. So now we don't have any problems. Okay. And if we run the batches, it's gonna complain that our libraries are not in the path. So the libtorch I want this one. Export ld library equals here. Now batches. Okay, so we have the same shape as we have in Python. To create the network, we need the number of features, which would be 28 times 28. I'm gonna include here the 1 because if in the future we change this to a multicolor image, then this number is gonna change. So I'm gonna keep it in the formula here. So in Python, we get the number of features by getting the shapes, exclude the 0 index. We transform it into a tensor. Then with the tensor, we can use this function prod that is gonna multiply all the elements, and we grab the item from the result of those multiplications. And we also need the number of categories. This from the train data here that we loaded. For all the targets, I'm getting the max value of all the targets, which would be 9. Then this is gonna return a tensor, so we need to get the item from the tensor, and then add 1 because this will return 9, but we need 10 categories. Depending on your data set, you might wanna use config ini to give the correct value for the categories. In C++, for this test batch here, I'm gonna get the data from the batch, get the sizes. So this is gonna return this 64 as we have here. So we need to slice it off. So this slice is gonna exclude the first element, and we are gonna keep all of this into this new variable. And then let me create the variable outside here, the for loop, and then we transform this sliced size into a tensor. We do the prod to multiply all 3 elements, and we get the result as an integer and store in this num features. To get the number of categories from the load data, we get the targets, the max value. This is gonna return a tensor, so we need to get the item, convert to integer, and sum 1. Again, if you have a different data set, these categories maybe should be better if it is in the config ini. Now we can start our network. So here, in the Python one. So here, our network is gonna get the number of features. It's the same network that we did before. So it's gonna receive the number of features, the hidden layer, and the number of categories, and I'm gonna tell it that now it's the train. It's the train stage, and the loss functions and the optimizers are gonna be the same as before. Loss functions NLL loss, and optimizer is SGD. For C++, our network is gonna be a pointer, so we need to create here as make shared a smart pointer, but we are gonna pass the same parameters, num features, the hidden layer size, and the number of categories, and we're gonna tell it that this is the train stage. For the loss function optimizer, they are the same, NLL loss and SGD optimizer. Here we can check if we have CUDA available. So if CUDA available, return CUDA. If this MPS is available, return MPS. If not, then return CPU. And set the network to use the correct device. In C++, we create the device, we check if CUDA available. If it is, we set the device to use CUDA. If not, we set to use CPU. I could not find this MPS in C++, so I'm not adding it here, but yeah, it does in Python. Now we can start training our network. First, I just want to get the size. This will be just for printing the results later. We just get the length of the training data that we loaded. Then we are gonna loop for the number of epochs that we configured here. In this case, I'm looping only 2. Then we are gonna get the batches here. So each loop is gonna be one batch, and this is just the batch index 0, 1, 2, 3, and this batch loader, as we saw here, it is a tuple that gives us the x and y. So we need to pass x and y to the correct device if we are using CUDA. We need to flatten our x, and we do the flattening with a new object here. So add this new flatten object, and it will flatten the x, because the x is gonna be like this 1, 28, 28, so we need to flatten it to 784. Here we forward x into our network. It's gonna return the predictions. From the predictions, we use it to compare with the correct labels, and we get the loss result. Then we do the backpropagation. We zero the gradient, we do a backward for the loss, and we step the optimizer. Then just for the each 100 batches, I want to print some values. So here from the loss item, I get the loss value. I have to, the loss is a tensor, so I need the item to get the value. And this is the current step that we are in, based on the size. So the size is gonna be 60,000. What is our current stage at the moment? So it's the index, the batch, and the size of x. Here we are getting the max index from the prediction, and we compare with the y to see if it's the correct label, and we convert it to integer. We sum all of them and we get just the item, so we know how many correct predictions we had in this batch. Then dividing by the length of y, we get the accuracy, and here we are just printing the data. In C++, these are some variables that we are gonna need. The size of the data, from the loaded data here, we get the size, and this we get the value. We loop through the epochs, the number of epochs that we defined. So we start again the index from 0. And we get the batches from the train loader. So this batch index is the enumerate here in Python. We need to have it as a separated variable here in C++. So we send the data to the correct device that we defined here. We also need to flatten x. Flatten is not defined yet, so create the flatten object like this. We forward the x values into the network to get the prediction. We compare the prediction with the y to get the loss. We do the backpropagation, we zero the gradients. We do the backwards propagation in the loss function, and we step the optimizer. Then for every 100 index, we are gonna print the values. So the loss value, we need to get the item, convert to float. The current step is the index times the size of x in the 0 dimension. So the number of batches in this loop. To get the maximum prediction, we use this torch and in the dimension 1, and this will return a tuple that we can get the values and the indexes. We compare the y with these indices to get just Boolean values. With the Boolean value, we can sum all of the Booleans and convert the final result as integer, and we have the count of correct predictions. Then from the count of the correct predictions, we can divide by the batch size, and then we just print the data here. Let's take a look here with the Python. So here, 2 epochs. At each 100 batches for each epoch, we print some results. Here, sometimes the accuracy can get really high, but we still need to pass in the test data, right? And the loss functions here, you see, it goes down, then a little bit up, but normal. And here, just printing the current stage. For the batches, we need to compile. Okay. We go to our terminal here, run. Again, 2 epochs. Every 100 we print some results, and the same logic from the Python code. So this data set here is a small data set, and we can do many iterations here, change the configuration and run again. It's not going to be much of a problem. But if you have a large data set and the training takes a lot of time, it's useful to save our network at the stage that it is with all the current values that it's saved in the network, in the hidden layers, the weights and the bias. So to save the data, we can save at each 100 batches here. So in Python, we get the state dict. So it's gonna grab all the values from the network, and here it's the variable that we passed here as the file name. And it's also nice to save it at the end after all the loops are done. In C++, we have almost the same thing, except that here we pass just the network, and the file here also we pass as a config ini, and it's good to have another save at the end. If you want to change the name and maybe include what's the epoch, then you change your script here. For this case, I'm just gonna save everything in the same file. Now that we saved our model, imagine that we are gonna start a new script from scratch just to test the data, because imagine that this took a long time to train our network. Now we are just gonna test the data. So we create our network, we pass the same variables here, the number of features, the hidden layer size, and the categories. We tell it to move to the correct device. If you need to copy this in your new test file, go ahead. So this would be the net loaded. I'm using a different variable just to not reuse the same here. And for this net loaded, we have to load the state dict from the torch that's gonna load the save model. So this is the file name. Here, the file name. Torch is gonna load this file, and then we pass as the dictionaries into the net loaded network. And now we tell our network that this is just for evaluation. We are not gonna train. So the network is not gonna update any weight or bias. To test, I'm gonna start with some variables here. I'm gonna tell Torch to not use gradient this time. Then from the test loader, the batches here, these batches, we pass X and Y to the correct device, if it's a CPU or GPU or CUDA. And we flatten X. We forward X into this loaded network. We get the predictions. We compare the predictions with the Y, the labels, right, in this batch. Then we get the loss item and we accumulate here in this variable test loss. Then for the prediction, we get what is the maximum index in the dimension 1 comparing with the Y. Convert to integer, we sum, and we get the item. So then we have the number of correct values in this batch. So we are accumulating all the results for all the batches in the test data. So then at the end, we need to divide the accumulated by the total number of batches. It will be like a 900. Then we get the total size of the data. For the accumulated corrected that we tested here, we divide by the size to get the accuracy. And now we have the test accuracy and results here. So we can test this now. So now our accuracy is more than 90% for the test, and we are testing all the 60,000 images. And here it saved the file for the network if we need to load it again in the future. Now let's do the testing on C++. Here we are creating also a new network with the same parameters. And here we load into the net loaded our save model. So this will be a file saved in the system that we pass here as the file name. And the data inside the file we load into the net loaded here. And we tell the net loaded that this is just for evaluation. We are not going to train. We're not going to change any weight or bias in this training. Here I'm starting some variables that we are going to need for the final result. So this situation here with Torch no grad, we are creating a new context here. So in C++, what we do is we just open these curly braces here, and then we can tell Torch to use no guard only inside these curly braces. Then we are going to loop through the test batches. We send the data to the correct device if it's CUDA, for example, or just CPU. Here we forward our new X here from this batch into the loaded network. We compare the predictions with the correct labels using the loss function. Then we get the loss value by converting the item to float values. Here to get the indices, we ask Torch to calculate the max into the first dimension here. It's gonna return a tuple. The first value in the tuple is the max values, and these are numbers 0 to 1. What we are interested is the indices, so we get the index 1 on the tuple. We compare the correct y with the indices that we got here from the max. This will return booleans, so we need sum, it's sum and convert to integer to get the count of correct predictions. And here I'm just gonna accumulate here the loss value into this loss variable here. The correct prediction I'm saving into this variable, and I'm increasing the number of batches. Pay attention that these variables are outside the curly braces because we are gonna use them after the curly braces. So the actual test loss we need to divide by the number of batches. We get the total size from the test data just to print the results. No. We get the size from the test data. And we use the size to calculate the accuracy based on the correct predictions. And here we can show our test results at the end. Now we just need to compile this. Okay, let's test. All right, here the saved file from C++, because we are executing the bin directory, and the accuracy above 90%. If you want to change here the number of epochs or the hidden layer, you can play around with this data. And see here, the Python took 44 seconds and the C++ took 88 seconds. The Python has to load the library here. The C++ has to load the library, but it spend more time on the build. So depending on your use case, maybe you want to stick with the Python because maybe you want to change quickly the algorithm here or your network. For the C++, these changes here are not compiled, so these are configuration, but the hidden layers, if here we are just have one hidden layer. If you want more hidden layers, then you need to recompile this again. But once you have established your network, then you get an increase on processing time. And if we change to CUDA, we could see better results and even speed up. So this is what I had to show you. The same algorithm in both C++ and Python. Please leave a like, share this series. If you have any questions, just write in the comments. I'll try to respond to everyone. So here I'm back on the Windows. I'm here just to run the latest changes that we did on the Windows. So let me revert here for the Windows variables, and let me open the Python, and let's run. Okay, yeah, we need to change the config, and here copy path raw, and here this guy, and we can run. Okay, ran the Python code. Now let's just reconfigure the project here, and then build. Okay, apart from these warnings, the build was success. We do need to pass in the update the path again. So here the libtorch lib get this path, and set, it was already saved here, and MNIST batches. Okay, the C++ code ran, saved the file here. This is the Linux execution, this is the Windows execution, and 48 seconds. It took a little bit time to load the libraries, but if we run this again, the library should be already loaded. Yeah, see now, second time 3 seconds, because the first time we need to load the libraries. So yeah, this is what I had planned for this project. If you like the series, remember to like the previous videos, like this video, and if you have any question, please add in the comments. I'll try to respond everyone. And thank you, and see you next time.